Welcome back. If you're just joining us, we are working through my Spring 2018 General Chemistry 2 test. Let's continue where we left off with problem number 7.
Problem number 7. So benzene has a boiling point of 80.1 degrees C and a boiling point elevation constant of 2.53 Celsius per molab. What would be the new boiling? So we know what the TF of the boiling is upon the addition of 40 grams of hexane. So grams of solute, 40 grams, C6H14, upon it dissolved into 150 grams solvent, or benzene. Now, the equation for this has to do with delta T equals I KB molab. I is our Van Hoff factor, which is a calculation of the degree of electrolysis, how many electrolytes form in solution. In the case of organic molecules, the degree of ionization, or the amount of electrolytes formed, is always 1. You dissolve hexane into benzene. How many hexane molecules does each hexane break into? It doesn't break apart. Any organic molecule will not really break apart. Only ionic bonds will break down. So we do not have to worry about this. So this I will be our 1 for this experiment. K is already given. So all we have to find to use this equation is N, molality. Molality is that weird cousin of molarity that no one really wants to talk about. Molality is defined as moles of solute over kilograms of solvent. So we don't need to figure out the total weight of solution, we just need kilograms of solvent. So in order to do this, we're going to turn grams of solvent into kilograms, and we're going to turn grams of solute to moles of solute. So the first thing, we can do this. There is 1,000 grams in 1 kilogram, so we have 0.150 kilograms of solvent. Now to turn grams of solute, we take 40 grams, C6H14, which has a molar mass of 86 grams per 1 mole. And that will give us 0.465 moles. So, going back to our molality, molality is 0.465 moles over 0.150 kilograms. Our molality becomes 3.1 molar. Now, we can plug our numbers into our equation. Delta T equals 2.53 degrees C molar times 3.1. This determines the change in boiling point to 7.84 degrees change. But the last step, this is where I would be willing to trick many of you, that you were not paying attention very well. You wanted to say, put that down as your answer. So what you need to think is, that's the change. What is the new boiling point? Because the change is T final minus T initial. So 7.84 plus 80.1 gives you 87.9, or answer letter B.
Continuing with problem number 8, we are looking at a property of solids problem. Which of the following solids would you expect to have a high melting point, low electrical conductivity, and high solubility in water? So a high melting point could be ionic, could be metallic, could be covalent, but not molecular. Low electrical conductivity eliminates metallic, but the high solubility means it must be a ionic, or answer A. For the next two problems, we need to refer to the phase diagram to the right. Notice that we have the units of Kelvin and atmosphere. Number 9, what would need to be done to achieve supercritical nitrogen from standard temperature and pressure? Standard temperature is 0 degrees Celsius or 273 Kelvin. Pressure would be 1 atmosphere. So at 273 Kelvin, 1 atmosphere, we are in the gas region. And so directly below the supercritical region. So we need to increase the pressure, or answer C. Question 10. At what temperature and pressure is the triple point achieved? So, and I say include the units. So looking at the triple point, it's that point where the liquid, the solid, and the gas come together. So that bottom left dot, that is about 10 to the negative first atmospheres. And that would be, say, maybe like 60 Kelvin. You have to look at the units, read the graph. 5 dashes between each 100, so each dash is 20, so it's about 60. There is some degree of error leeway in there. Okay. Problem 11. Which intermolecular forces are present in the following compound? So we see a CH3 bound to a pH2. Got to look at those compounds. CH3, pretty nonpolar. pH kind of looks like it could be polar, but it's not really one of the ones we've mentioned before. And so you might want to say it's hydrogen bonding, but in order to have a hydrogen bond, we need an NH, a OH, or FH. P is not actually really polar, so really the correct answer is D, just London dispersion forces. Moving straight on to problem 12.
Problem number 12. What would the osmotic pressure be if 30 grams of sodium sulfate is dissolved into 1 liter of solution at 25 degrees C? So this is a standard osmotic pressure problem. The equation for osmotic pressure is defined as osmotic pressure is equal to the Van 't Hoff factor times R times T times M, our molarity. This is because we are essentially saying pressure equals nRT over V. And this part is being turned into our molarity. So it's just a manipulation of the ideal gas equation. Our molarity is once again moles over liters. I state that our volume is 1 liter. Our mass of our solute is 30 grams of Na2SO4. Our temperature is 25 degrees C. And the answers are in atmospheres. So that should tell us something about our ideal gas constant. For our ideal gas constant, we want 0.08206 atmosphere, liters, moles, Kelvin. Now that K tells us a lot about that temperature. That temperature needs to be in Kelvin for this to work. So we're going to start by adding 273. Get it add to 298 Kelvin. Now the only thing we need now is molarity. Molarity, 30 grams of sodium sulfate. Sodium sulfate has a molar mass of 142 grams per mole. So 30 grams, 142 grams in 1 mole, 1 liter. It's going to give us our molarity of 0.211. Before we plug everything in, we must consider our solute. This is no organic compound, but this is our standard ionic compound that we learned early on last semester. Sodium sulfate. Each sodium is going to be an individual atom. So we have 2 sodium atoms. Now don't be overly chalk happy. Even though we have 1 S and 4 O's, that sulfate will remain an individual unit of SO4 2 minus. And so, how many ions would form upon dissolution? We would form 3 ions. So I is equal to 3. So plugging our numbers into our equation, we get 3 times 0.08206 times 298 times 0.211. Plug those in, and you would get 15.5 ATM. A rather large osmotic pressure. For answer B.
Well, that is the end of page 2 of this test. I hope to see you again as we finish this test on page 3.